Good evening everyone. I welcome you to the 7th problem solving session of NPTEL course Combinatorics. So today we'll be discussing few combinatorial problems from graph theory. Let's begin. So our first problem says that we are given a regular connected graph G with 22 edges, and now we have to find the possibilities of number of vertices. So now first of all let's recall. So graph recall graph was a collection of vertices and edges. Vertices we were denoting it by v1 vk, and edges were two, like we pick any of the two vertices, so it was two element subset of the set of vertices. So edges were this, and second, by regular graph we mean that degree of each vertex is same, and by degree we means, so if we have a, say if this is my graph, so the set of vertices will be v1 v2 v3 and v4. Edges will be v1 v2 v3 v4 v2 v3 and v2 v4. These are my set of edges, and my vertices were v1 till v4. So by degree we mean that, so by degree we mean the number of edges which are incident to each vertex. So we can see there are two edges incident to v3 v2 and v3 v4, so degree of v3 will be 2. And by regular graph we mean that degree of each vertex should be same. So we can see that this graph is in this particular case this graph is not regular, because degree of v1 is 1 and degree all other degrees, degree of v1 is 1 and degree of v4 is 2. So we see that two vertices have different degree, therefore this graph is not regular. So and thirdly, it says that the given graph is connected. By connected we mean that between any two vertices we have a path. Any two vertices, there exists a path or a walk. There exists a walk between any two vertices vi vj. There exists a walk starting at vi ending at vj, and walk is basically, you are going walk is what you'll imagine it to be. So if you want to see a walk from v1 v4, so you are basically going from v1 to v4 through some edges. And difference between a walk and path is, so in walk anything can happen, but in your path no edges should be repeated. So this was the term that we need in the question. But now the question says that we are given a regular connected graph. G is regular plus connected. Moreover, it has number of edges is 22. So we want to know how many vertices, we want to find the number of vertices. So we have a nice relation between vertices and edges, which is as follows. 2 times sum of edges is, if we sum the degree of each vertex, and this is also straightforward, because given any edge v1 v2, each edge is contributing 2 2 to the LHS, because one it is one it will add plus 1 to degree of V1 and degree of V2. So we see any edge in a graph contribute 2 degree. Therefore, this is the equality. So now, suppose we have this. So now we want to solve this. So let number of vertices of G to be n, and since G is regular, we can say degree of any vertex. Let degree V equal to D. Let degree V equal to D for any V. And now if we plug these value in the above formula, we'll get that 2 into 22 is equal to, we are summing over degrees, so V belongs to G and the degree is D, and we have, since and the number of vertices is n, so this is ND. So we see that ND is equal to 44. Now both n and d are natural numbers. So what are the possibilities for n and d? So n should, so first thing that we can deduce from this, that n should be a factor of 44, because both of them are natural numbers. So what are the possibilities of n? It can be 1, 2, 4, 1, 2, 4, 11, 22 and 44, and corresponding to them the degree value is 22, this is 11, D is 44, 22, 11, 4, 2 and 1. So now we want to see what, so we have got that this is n and this, but any set of pairs n d won't guarantee that we'll have a graph. So we'll now look case by case and see in which case we can say that we'll have a graph, and in which case we can totally say that there won't be any graph. So case 1, we see n for n equal to 1 and 2, 1, 2 and 4. Since degree is greater, since d is greater than n, this can't happen, because degree of vertex is at most the number of edges minus 1, number of vertex minus 1. Because if you have a vertex v1 and if you want to compute its degree and you have n vertices, it can meet in, and we are talking about a simple graph, so it can meet each vertex at most 1. So we see that degree of vertex should be less than equal to n minus 1. So n equal to 1 to 4, this can't happen. Now we see the remaining cases. So first, if n is equal to 44 and d is equal to 1. So now since d is equal to 1, this says that there exists unique edge, from each vertex, and this can happen only if G is like this. We have V1, V2, V22 and this is V21, V22 till V44. Only we have, this is the only possibility. And clearly G is not connected. So this cannot happen either. Because degree is 1, we have there is only, so you get, there is only one vertex, and this is the only case possible. So we see that this also cannot happen if n is equal to 44 and d is equal to 1. Now we are left with two cases, when is n is equal to 22, d is equal to 2, and n is equal to 22, n is equal to 11, and d is equal to 4. So n equal to 22 and d is equal to 2. So this says that if you have a vertex v1, we have two vertex coming out of it. Because the degree of v1 is 2, so we'll have a vertex here and we'll have a vertex here, and we'll have no more vertices. Similarly for v2, now we have already have a vertex 1, so we can have one more vertex. So we see here the only case is possible is the cycle of 22 vertices, which is connected. So n can be 22. Now we have n equal to 11 and we want that d is equal to 4. We can see this is also possible, because okay, so if you have, so you have to basically give a, so if you have this v1, v2, v3, v4, v5, let's see this. These are the 5 vertices and you are ordering them in some manner. So basically you can construct this, join v1 with v3, v2, v3 and v4. Sorry, I mean to say, so we have to construct the graph. So if you have this v1, so first you join it with its immediate neighbor v2 and v3, then you join them to the second immediate neighbors. So you will construct this, and if you do this for all vertices, you will get a graph, you will get this required graph. So we see that the possible answers for this are 22 and 11. Now the second question. Before reading out the question, I want to explain few terms that will be used in the question. So first, and some of the terms you might have encountered during the lecture. So tree. What is a tree? So tree is basically a connected graph without any cycles. And cycles are basically closed loops. So something like this is a tree. But if there is a closed path, this is not a tree. So a tree is basically, it has to be connected and it should not have any cycles. Now another thing is a rooted tree. So rooted tree is a directed tree with a distinguished vertex, which we call root, vertex called root. And what speciality that vertex has? It has no in degree. That means all edges go out of it. There is no edge coming on it, coming in it. So it has no out degree. So this is a directed tree and this is a root. So a rooted tree is a directed tree with a distinguished vertex. Now a complete K-array rooted tree. So it is a rooted tree such that every vertex has 0 or k children. Every vertex has 0 or k children. So now, what do we mean by a children? So children refers to the edges going out from a vertex. So as I have an example, so this is an example of 3-array tree, 3-array rooted tree. So this is a root and you see all the vertices are coming out of it, and the number of vertices coming out from each vertex are either 3 or 0. And under this 3-array tree also we have two types of vertices. First are leaf or non-leaf vertex. So leaf vertex is basically the vertex which are at end, something no out degree. And non-leaf vertex has out degree 3. Or out if it is a complete K-array tree, out degree k. So now once we have set up all these notation, now the question is saying that given a complete K-array tree, given a complete K-array rooted tree, suppose this complete K-array tree has m non-leaf vertices, we have to find number of leaf vertices. So what is the question? That suppose T has m non-leaf vertex, find number of leaf vertices, sorry, this is plural, find number of leaf vertices, or in other words leaves. We can call it either leaf vertices or leaves. So first let's do it for some smaller n, and then we'll see if we can generalize it. If m is equal to 1, so if we have a rooted tree, we'll have to have a root. So suppose this is my root. Now m is equal to 1, that means T has exactly one non-leaf vertex. And since this T is a K-array rooted tree, out degree of each vertex is either 3 or 0. But since T has exactly one non-leaf vertex, so degree of this vertex cannot be 0, because then this graph will have just one leaf. But we want that T should have exactly one non-leaf vertex. So it cannot have out degree 0. So what is the next possibility? It will have out degree 3. And now we see we can now all the new vertices that we have, they cannot have any more children, because because if any of these vertex will any of more children, then it will also become a non-leaf vertex. But we want that T should have exactly one non-leaf vertex. So this is the only possibility. So for m equal to 1, number of non-leaf vertices are coming out to be 3. So suppose by notation Lm denotes the number of leaves when number of non-leaf vertex is m. So from this we see that L1 is equal to 3. Now if m is equal to 2, so if m is equal to 2, we start with a root. Then also now it cannot have, because we need at least 2 vertices, it cannot have degree 0. So this vertex will have degree 3. Now in this diagram, in this graph, number of leaves is 3, number of non-leaf is 1. But we want one more non-leaf. So at least one of so we want one more non-leaf. So exactly one of these 3 vertices will be a non-leaf. So the next step is make one of the vertex, exactly one of the vertex non-leaf. One of the vertex which is a leaf, a non-leaf. So the number of leaves then will become, number of non-leaves will become +1. And now if we have to make exactly one of this vertex non-leaf, that means this one of this vertex, suppose this, like without loss of generality, let's assume this is the vertex. So this cannot have degree 0. So if this cannot have degree 0, it has to have out degree 3. So it cannot have out degree 0, so this will have out degree 3. So if it has out degree 3, so when we make exactly one of the so in this step, when we are making one leaf a non-leaf, what we are doing, number of non-leaves is becoming +1. But what is happening to number of leaves? So we are making one of the leaf non-leaf. So basically we are subtracting -1. And now when we are making a leaf, we are adding the k branches. So these should be k. Number of leaf, so I was doing it for a 3-array tree because we were doing it for this, but this 3 can be replaced by k also. So whatever I did was I did for 3, but the same reasoning follows for k. So we see number of, what is happening to this number of leaves, this is becoming -1. Okay, let it be 3-array only, because I have done this for 3 also. So we started with a root, then it cannot have this. So this was why it is 3, because we are talking about a 3-array tree, 3-array complete tree. So now again 3. So what we are doing, end result is number of leaves are getting subtracted by -1, and then we are adding 3 more leaves. So in general, that is when k is general, if Lm denotes number of leaf in a k-array tree which has m non-leaf vertex. So from our previous reasoning, what is Lm? It is the, so we have Lm -1. So first we construct a tree with m-1 non-leaf vertex. So this will give us Lm -1. This will gives L m minus 1 leaves. Now to get m non-leaf vertex, we make one of the leaf in Lm minus 1 non-leaf. And in doing so, what we have, so we are subtracting one leaf from the Lm minus 1, and when we are making a leaf, a non-leaf, so we are adding, so this if it is a non-leaf, it has degree 0. If it is a non-leaf, it has degree 0. If it is a leaf, it has degree 0, and if we have to make it non-leaf, then the out degree of this has to be k. So we are adding k more leaves. So we see that we are getting a recurrence relation like this, where Lm is equal to Lm minus 1 plus k minus 1, and this we see this sequence L1, L2 so on is an AP, where our first term is L1, first term is k, which we have computed, and common difference is k minus 1. So what is Ln by AP formula? It is just first term plus n minus 1 into common difference, which is k plus n minus 1 into k minus 1, and if you further solve it, you get it k plus nk minus k minus n, which is plus 1, which is k get cancelled, and you are left with n k minus 1 plus 1. So this is our final answer. So given a k-array tree with m non-leaf vertices, the number of leaves are n into k minus 1 plus 1. Okay. Now next question. So our next question says, we have to find maximum number of edges that a disconnected graph with n greater than equal to 3 vertices can have. So what we have to do, we are given a graph G with n vertices, we need to find maximum number of edges. Given a graph G with n vertices, disconnected graph, we need to find maximum number of edges that G can have. So, okay. So this is just like motivation to guess the result, kind of. So suppose, firstly, suppose condition of disconnectedness is dropped. Then what is the answer for the same problem? That is maximum number of edges for G. Maximum number of edges for G if we have no conditions on G. Then G will have all possible edges. That is, G will be equal to Kn, or G will be totally connected. So complete graph, it is kind of a best possible connections. So we see connectedness, best type of connectedness is maximizing number of edges. Now we want to maximize edges for a non-connected graph. Previous observation that this Kn is maximizing the edges shows that least disconnected graph this is just for motivation. By least connected graph means for the graph which is kind of connected but which is forced to made connected, which is forced to a connected graph which is being forced to have disconnection, might give the answer. So if we want to might give the answer, so what is the best, what is the least connected kind of thing? So if we have v1 vn, so if we take v1 as to be the one vertex which is isolated and v2 vn minus 1, they are totally connected, then this graph G is disconnected and G has how many edges? So no edges are coming from V1, all the edges are coming from V. G has G has number of edges of Kn minus 1. And what are the number of edges of Kn minus 1? They are just n minus 1 choose 2. They are just n minus 1 choose 2. So we see that the maximum number that we required is greater than equal to n minus 1 2. Choose 2 because we are able to construct a disconnected graph of n vertices with n minus 1 choose 2 edges. Now the claim is, this is the answer, that is, if a graph of n vertices has n minus 1 choose 2 plus 1 edges, then G is connected. And if we show this, if we prove this claim, we are done. The number that we required is this, that is, a disconnected graph with n vertices can have at most n minus 1 choose 2 edges. Because if a graph has n minus 1 choose 2 plus 1 edges, then it stops being disconnected. It has to be connected. Now we'll prove this. Proof of claim. We'll prove it by induction. If n is equal to 3, this is clear. Why? If we have 3 vertices and if we want to construct a disconnected graph, it cannot have two edges. It has to have one edge. And you see that 3 minus 1 choose 2 plus 1. Oh, sorry, plus 3 minus 1 choose 2 is 1. So if a graph of 3 vertices has two edges, it is connected. So for n equal to 3, we see that this is trivial. Now we are assuming for n to show for n plus 1. What do we need to show? That given n plus 1 vertices and n choose 2 plus 1 edges, G will be connected. So pick a vertex. Suppose V1, Vn plus 1 are the vertices. Pick a vertex V. Say V1. Then first of all, degree of V is greater than 0. Why? Because if degree V is equal to 0, then all edges are coming from V2 till Vn minus 1. So number of edges, complete graph on n minus 1 vertices has n minus 1, V2 till Vn plus 1. So this has n, these are n edges. So number of edges on maximum number of edges for graph of n vertices is n choose 2. So number of edges should be less than equal to n choose 2. But here our graph has n choose 2 plus 1 edges. Therefore we know that degree V has to be greater than 0. Now suppose degree V is equal to n. If degree V is equal to n, then clearly G is connected. Because given V1, V2, if degree V is equal to n, V is connected, V is incident to every other vertex. Therefore, we can, given V1, V2, we can find a path V1, V2. Therefore, we see that if degree V is equal to n, then it is connected. That was the maximum possible degree. So now the remaining case is when degree is lying strictly between 0 and n. For 0 it is not possible, and for n we have shown that it will have to be connected. Now we have to show this. So we have a graph. So what is the situation? We have a vertex V. We have vertex V2 till Vn, and this V has degree less than n and greater than 0. So now we have to use induction, right? So consider G dash, which is the subgraph of G, subgraph induced by V2 till Vn. And now number of edges in G dash will be number of edges in G minus degree of V. Because if we have to take a subgraph induced by V2 till Vn, we have the, so basically we are considering all the edges which are in G and are coming from either of this vertex till V2 to Vn. So what are all edges we are removing? The edges which contain V. And what are the number of edges which contain V? They are just the degree of V. So we see that number of edges in G dash is this, and degree of V is less than n. So we see that number of edges in G were given to be n choose 2 minus 1, and degree V is less than n, so minus dV is strictly greater than minus n. So the number of edges in G dash is strictly greater than n choose 2 minus 1 plus n, and this is nothing but n wait, so we have minus 1 minus n, so this is n choose 2 minus n plus 1, and this is nothing but n plus 1 choose wait, there is some issue. So we have degree V is n, number of edges in G, number of edges in G were n choose 2 plus 1. Okay, yeah, now I get it. This was plus 1. So this term now becomes n choose 2 minus n plus 1, and which is nothing but n plus 1 choose 2. There is still a problem. This should be n minus 1 choose 2, n choose 2 minus n minus 1. So what we have this equality that n choose 2 minus n minus 1 choose 2. We are basically using this. N choose 2 minus n minus 1 choose 2 should be n minus 1. So now this term is basically n choose 2 minus n minus 1, which is nothing but n minus 1 choose 2. So we see that G dash is a graph with n vertices and greater than n minus 1 choose 2 edges. Therefore, by induction hypothesis, G dash is connected. Moreover, degree of V is greater than 0. Therefore, V is connected to G dash. V is connected to G dash at least by one vertex. Now G dash is connected and V is connected to G dash by one vertex. So we see, therefore G is connected. And hence we have shown our claim. And once we have shown our claim, we have shown that answer is graph disconnected, graph with n vertices can have at most n minus 1 choose 2 edges. And what is the example for such a graph? You take one to be an isolated V1 and another as Kn minus 1. So this was your question. Okay. This was all for today. Thank you.